This podcast is about the theory of covalent bonding and how it fits together and makes covalent molecules. So covalent bonding is when two atoms share electrons, and the simplest molecule with a covalent bond is hydrogen, and hydrogen is made of two hydrogen atoms, H and H, and it gets together and makes H2. Each hydrogen has one valence electron, and then as they get closer, they overlap, and the electron of one hydrogen is attracted to the nucleus of the other hydrogen, and that's why they overlap. We draw it like this, circle here to show that it's overlapping, and each electron is attracted to both nuclei, so they share the electrons. When we're counting electrons in a covalent bond, each atom gets to count the shared electrons. And the octet rule is satisfied because both hydrogens have 2 electrons. Each of them gets to count 2 and has a filled energy level. A lone pair is an electron, a pair of electrons. It's not bonded. It just sits on one atom. It's not shared. So here we're going to show how fluorine bonds. Each fluorine has 7 valence electrons. As they start to overlap, the 2 unbonded electrons, unpaired electrons, overlap with each other. We draw it like this. It's a single bond, which is 2 electrons. Now each fluorine has 8 electrons surrounding it, so it satisfies its octet. We can also draw it this way, with the line in between the 2 fluorines to show that those are the 2 electrons that make the bond. So now we're going to look at oxygen. And oxygen, each oxygen atom comes with 6 valence electrons, so each has 2 electrons that are not paired. They overlap. We get a double bond, which is 4 electrons. Again, each oxygen is now surrounded by 8 because I remember that we double count the ones that are shared. So each oxygen has 2, 4, 6, 8 electrons. And we can also write it like this, with the shared electrons as lines, bonds. A little bit easier to see here. Last, we're going to do nitrogen. Each nitrogen comes with 5 valence electrons. 3 of them are going to get overlapped to make a triple bond, which is N2, and the triple bond can be drawn with 3 lines here. Again, after we're done with the structure, each nitrogen has a total of 8 electrons surrounding it. So if we're going to compare some data on bonds, single bond is, for example, carbon-carbon. It has a bond order of 1. It uses 2 electrons. Here's its length, 154, and here's the bond energy. It takes 347 kilojoules to break this bond. If we compare it to a double bond, which has a bond order of 2 made of 4 electrons, it is a little bit shorter, 134, because it has better overlap. And it is a little bit stronger because, again, it has more electrons overlapping, which makes a stronger bond. This continues with a triple bond, C triple bond C, bond order of 3, 6 electrons, shorter still, 120, and a stronger bond still. So the covalent bond energy is the energy that's required to break a covalent bond. It's typically in units of kilojoules per mole. And the distance between the nuclei is the bond length. This is the most stable distance. It balances the attraction that the atoms feel with the repulsion that happens if the nuclei get too close together. We see that in this energy diagram. This is potential energy. These are the atoms really far apart. They're attracted to each other, so the energy goes down, which is good. If they get too close together, the energy shoots up, which is bad. The most stable place is the lowest energy configuration, and that's the bond length. So let's look at some bonds. If we were to rank these guys by length and strength, if we look at sulfur bonded to fluorine and bromine and chlorine, SF would be the shortest because fluorine is the smallest atom. SBr would be the longest because bromine is the biggest. And the shortest atom is the strongest. Shortest bond is the strongest, SF. SBr is the longest and it's the weakest. We compare single, double, and triple bonds. For CO, the shortest is the triple bond. The single bond is the longest. The strongest bond is the triple bond. The single bond is the weakest.